Here's an array. Kadane's algorithm says this subarray is the max sum. But its length isn't divisible by k, it's disqualified. So the real answer is hiding somewhere else entirely. You climb through the array looking for the subarray whose sum is the biggest. But with one twist, you're only allowed to pick subarrays whose length divides evenly by a given number, k. Given the array of numbers and that value k, the goal is to find and return that maximum possible sum. Hey, I'm Kai, and this is Fun with Learning Technology. Here's our array, -5, 1, 2, -3, 4. With k equals 2, the answer turns out to be 4, coming from the last 4 numbers. The obvious move is to check every possible subarray, add it up, and throw out any whose length doesn't divide by k. That works, but for n numbers, you're looking at roughly n squared subarrays. For 100,000 numbers, that's billions of sums. We need something smarter. Build a running total as you scan the array. The sum of any subarray is just one running total minus an earlier one. So maximizing a subarray sum means maximizing that difference. The endpoints of our subarray have to be k, or 2k, or 3k apart, always a multiple of k. In prefix sum terms, that just means the two indices leave the same remainder when divided by k. Split every index into k buckets by its remainder mod k. Two indices only qualify as endpoints if they land in the same bucket. Inside each bucket, we just want the smallest earlier prefix sum. It's easy to bucket prefix sums by their value mod k because that's the trick from Subarray sums divisible by k. A different problem where the sum itself has to be divisible. Here the length has to be divisible, so what matters is the index, not the value. That's why we bucket by index mod k instead, and only let a bucket's minimum become eligible once we've moved k steps past it. First, we build the running totals in one pass. Prefix at position I plus 1 is just prefix at position I plus the next number. That single array is all we need for every subarray sum from here on. Now the one pass that does the real work. Before touching bucket R, we check if the index k steps back is old enough to count, and if so, fold its prefix sum into that bucket's minimum. Then we compare our current prefix sum against that minimum and keep the best difference we've seen. That's the whole thing, start to finish, one pass. No nested loops, no rechecking old subarrays, just running totals and a bucket per remainder. Let's run it on our actual numbers. Best stays empty until I reaches 2, when bucket 0 finally has a value to compare against. It climbs to 3, then settles at 4 once we reach the end, matching the answer we expected. Brute force was checking every subarray, roughly n squared work. This one pass, one loop, constant work per step is just big O of n, and big O of k extra space for the buckets. Prefix sums. Turn subarray sums into a simple subtraction. The length rule just tells you which prefix sums are allowed to pair up. Bucket by remainder, delay by k, and one pass finds your answer. New daily, drop tomorrow, same time. If this one clicked for you, the subscribe button's right there. Quick one before we go. What's the time complexity of the approach we just built? Pause and think it through. Take a second. Really think about how many buckets we touch and how many prefix sums we compute. It's linear time, one pass to build prefix sums. One bucket check per index, k buckets total, no brute force nesting. Second question, if k is 3, but the array only has 2 elements, can a valid subarray even exist? Pause and think. Think about the shortest subarray length that's divisible by k, and whether the array is even that long. No, it's impossible. The shortest subarray divisible by k has length k, so if the array is shorter than k, there's nothing to find. Talk is cheap, let's actually run this. I fed it all. 3 of the problems real examples, no cherry picking, plus 3 extra edge cases I picked myself. Let's actually time both. Brute force took 690.09 milliseconds. The optimal version took 1.87 milliseconds. That's a real 369.5x from actually running both just now, not a complexity estimate.